So this week we only have 3 days of class because you guys have some kind of AP test on Friday. So I'm giving you Thursday and, of course, Friday off so that you can focus on doing final review for your test and then taking the test itself. As somebody who's been taking large, difficult exams his whole life, I would recommend that no matter how you feel about your test on Friday, you don't spend that much time on Thursday studying for it. Studying for a test the day before like that is usually a recipe for failure. The work for how you are going to do on that test is mostly already set in stone. So you should actually just spend that day before working on your own like mental health and comfort. Spend the day before relaxing, get some exercise, have a good meal, go to bed early. That stuff is more important for your final AP test score than, I don't know, desperately trying to cram a few chapters out of the book. Now, in these like 3 days leading up to Thursday, you probably have a little bit of a chance to affect your test score. There is some value in studying 5 days out, but not 1 day out. Nonetheless, today we have a warm-up. So today for item number 1, I would like you to take the sum of the series. And for all 3 of these, not only do I want you to take the sum of the series, but before you do any of these, also please write them in sigma notation. So for item number 1 here, given the series 10, 8, -1, I need you to go through and I need you to add up the first 750 terms. Item number 2, I have some series 1, 3/2, 9/4, etc., etc., etc. For that one, I need you to add up the first 29 terms. And then for item number 3, we have some series 200, 150. I need you to add up every single term for that series, all of them, from the first term down to the final term. Yeah. Take a few minutes and then we'll go over this together. Yeah. And in the meantime, I'm just gonna wait a little bit for more people to roll in here. We have a few missing. You guys ready for your AP tests?
Almost, I think so.
Yep.
For most of us.
That's good.
Just a little bit more like here and there, just practicing.
Yeah, which one's on Friday?
History.
US history.
Which textbook did you guys use for that class?
ABSCO.
Not the American pageant?
No.
Okay. Let's go ahead and start, and we're gonna do a little bit of vocab here on top of just what we're doing. And this is actually like a compound question because in order to do these, it's not enough to just take the numbers that are given. For any of this stuff to work out, we actually have to write out the explicit series that is generating these terms. So let's just go ahead and start off with vocab. What kind of series is number 1?
Arithmetic.
Yeah, item 1 is arithmetic, and we know that because between these terms there exists some kind of common difference, not a common ratio, and luckily you guys are only responsible for dealing with these 2 types of series, though you should know that like this type of mathematics, which is called set theory, like how do large groupings of numbers behave so long as they are bound by a rule. This is an entire elective you guys can take if you major in math. So if you happen to like choose to major in mathematics or applied mathematics, when you guys get to your junior or senior year of college, you can take this stuff for 10 weeks straight. So it's arithmetic. That's pretty clear. And then is this finite or infinite?
Infinite. Oh, just for the first 750 terms.
Yeah, this is finite. And this isn't something that I said explicitly in notes. This isn't something that I had you guys transcribe, but I think it's important to notice right off the bat that there is no such thing as an infinite arithmetic series. It's not a thing I defined or gave an equation for, simply because you can't intelligently analyze an infinite arithmetic series. You'll always get one of two possible answers if you are actually trying to deal with an infinite arithmetic series. We'll talk about that a little bit today in our notes. Last time, we got through all of the vocab and all of the equations that we needed, but we didn't quite get to a place where I felt comfortable stopping. So today we're going to do a little bit of notes on infinity. Item number 2, what kind of series is that?
Geometric.
Yeah, that's geometric. And how do you know it's geometric?
It's getting multiplied by 3 over 2.
It's not really a difference.
Right, it has a clearly definable common ratio. That is to say, in this first jump, right, there are 2 ways that we can go from 1 to 1.5. I could either add 1/2 or I could multiply by a number. To see if this actually is a common difference, we'll see if the difference is kept the same. So to go from 1 to 1.5, we're adding 1/2. So if I were to add 1/2 again to 1.5, then this would be 2. If this was 1, 3 over 2, and then 2, that would tell me that this is arithmetic. Since it's not arithmetic and this, section only contains 2 different types, kind of by default, I know that this is geometric. Or we could take this, divide it by that, realize that we're getting multiplied by 3/2, and notice that this times 3/2 would give us 9 over 4. So this is geometric, and is this finite or infinite?
Finite.
This is finite. And that is simply because I'm asking you to add up the first 29 terms and then stop. If I were to ask you to calculate some sort of infinite geometric series for this particular geometric series, it can't be done because the common ratio here falls outside of the boundaries of a definable infinite series. And then here, add up every term. So is this geometric or arithmetic?
Geometric.
It's geometric with a common difference of
1 over 2.
And is this finite or infinite?
Infinite.
This is infinite. I'm asking you to add up all of the numbers that exist within this set. And interestingly enough, because this R happens to fall within the boundaries of what is possible for doing a geometric, an infinite geometric series, because R is less than 1 but greater than 0, then we say that this is a converging geometric series. And even though I'm asking you to add up an infinite number of numbers, the sum of that infinite number of numbers is still a finite value that we can define. So let's go ahead and do this. So item number 1 here, we're being asked to add up all of these digits. And so we're being asked to, we're being asked to take the sum from the first value to the 750th value. So we draw our little sigma with n equals 1 below and 750 up above. This is where we start adding. This is where we stop adding. And then what is our explicit series? We're going to need the explicit generator of this set if we want to take the sum. What do we get out there?
9n plus 1.
So it's going to be, careful there, negative 9n.
Oh, right. Yeah, it's decreasing.
It's decreasing by 9 each step if we're going from 10 to 1 to negative 8. And then what is our constant? You plug in 1 and you get 10. So what does our constant have to be?
11. Or negative, no.
Plug in 1 and you get 10.
Well,
so if I
19,
plug
right?
in 1, it'll give us negative 9. So the constant is 19, correct?
19.
Yeah. And of course, if you're not feeling initiated in this type of mathematics, you do it explicitly. You plug in 1, you get 10, you solve for that constant. The constant must be 19. Are there any questions on how this and that are identical?
No.
Okay. And so if we want to calculate our series, nobody's asking you to take 750 digits. If you're sitting there, if you started when I wrote this question down and you started listing out all 750 values, if you're doing that without some sort of like mechanical assistance, like an Excel spreadsheet or a clever loop written into your graphing calculator, you're still not done. That's why for the calculation of these types of series, right, we rely on various formulations, which can be proven using set notation, that this series is calculable by some trickery. And so what is our series equation for an arithmetic series, which is, you know, based on the childhood work of Gauss? It's the first term plus the last term multiplied by?
N over 2.
Multiplied by the number of pairs that have that sum, correct. So we need to calculate the first term, we need to calculate the last term, and then we'll realize that, you know, all of the digits in this set pair off in a specific way, and the number of numbers divided by 2 is equal to the number of pairs. So this is asking us if we're going to do, sorry, I'll write it out, the equation first. This is to say that the sum of the series for n terms is equal to n over 2, the number of pairs, then multiplied by the first term plus the last term. So if we want S sub 750, so add up the series up through the first 750 terms, this is going to be equal to 750 divided by 2, our number of arithmetic pairs, times our first number, a sub 1, plus our last number, a sub 750. We plug in what we have, so this is going to be equal to 750 divided by 2 times 10 plus, what is our last number? What is our 750th term? What is our 750th term? If we add, I'm sorry, if we subtract 9 again and again and again and again and again and again, 750 times, what do we end up with?
Negative 6,731.
And of course, we're not actually subtracting 9 750 times because we're not dumb, right? So how are you getting that this is negative 6,731?
You need to use the equation.
Right. That is the whole point in coming up with the explicit series, so that instead of you know, actually subtracting 9 again and again and again and again and again, you just multiply. And so, you know, computing whatever this value is will give us what the first 750 digits of this series add up to. What are we getting out there?
Right.
And so I think it's a nice natural answer, right? Every time we are going to larger and larger and larger and larger and larger negative numbers, and we're being asked to take increasingly growing negative numbers and add them back to ourselves or themselves. So in the end, our sum should be some extremely large negative number. Are there any questions here on item number 1? Any questions out there on item number 1? No? Okay.
So.
Okay. Item number 2 here, we're being asked to take a finite geometric series for the following, for the following, I guess there's nothing else to that sentence. We're being asked to take the following finite geometric series. Yeah, that sums it up. Anyway, that means that for item number 2 here, number 1, we're going to write it in sigma notation. So we have to take this homie and we have to sum it from n is equal to 1 all the way up to n is equal to 29. And before we do that, we're going to need our explicit series, just because it makes it that much easier to analyze this object. And so what is our finite geometric series? It's going to be the first term multiplied by the common ratio raised to the n minus 1. Our first term is 1, and what is our common ratio?
3 over 2
over
to the
2.
power of n minus 1.
3 over 2, then raised to the power of n minus 1. So this equation right here will generate all of these terms forever. And so to do our finite geometric series, again, for a finite geometric series, we have some specific equation based on a proof. If you're very clever, you take the definition of a series, you multiply by the common ratio and subtract that from the original equation, and you can show that a finite geometric series, S sub n, must be equal to the following. The first term, a sub 1, multiplied by 1 minus the common ratio to the n, then divided by 1 minus r. The proof that produces this, I think, is one of the most elegant things in all of pre-calculus that isn't all of that stuff from trig. Like that stuff from trig, beautiful equations, works out real nicely, has a lot of information within it. This is also one of the most elegant manipulations you're exposed to before calculus. Nonetheless, yeah, all we're being asked here is to add up the first 29 terms. So that is to say that the series sub 29 is going to be equal to a sub 1, which in this case is just 1, multiplied by 1 over our common ratio, 3 over 2, raised to the 29th power, then divided by 1 minus 3 over 2. And the correct calculation of this will give us what the sum of the first 29 terms is. Uh,
255.
Here, parentheses are crucial, so make sure that you have your parentheses. And that would be to say parentheses here around the 3 over 2 before you raise it to the 29, and also one set of parentheses around your numerator before you divide it by what's going on in the denominator. And what you should get is 255,666.079. The decimal coming from the fact that these are fractions, so by the time that you get to the 29th term, we are terminating on some kind of decimal. But you'll notice here that geometric series grow way faster than arithmetic series do over a small range. So, you know, this 2 million is made out of 750 terms. We're already approaching a million just within the first 29 terms here. So typically when I give requests about geometric series, the numbers are going to be smaller, but that's not because I expect you to do this by hand, right? Like I said, ain't nobody asking you to add up 29 numbers by hand or with a calculator or whatever. It's just because if this number were to go much higher, if this were to go to 100 or whatever, you would get to a point where entering it in your calculator won't give you anything back, simply because your calculator will have an overflow error. The number will get so big that the RAM can't calculate it. Any questions on item number 2? No? Okay. Item number 3. We are being asked to calculate some sort of infinite geometric series, which, as we learned on Friday, is possible that you can actually take up an infinite number of numbers and add them up and get a finite value. So again, we're going to take this guy right here. We're going to write him in series notation. So that is to say that we are going to take the sum from n is equal to 1 all the way up until the last number that can be calculated, right? Which is infinity terms out. And we are going to take this series for the following generator here, 200, 150. So what do I write? Our first term is 200, and what's our common ratio?
Negative half.
1/2.
Yeah, negative 1/2.
1/2. If it was negative 1/2, it would be 200, negative 100, positive 50, negative 25, and for that type of series, you cannot take an infinite sum.
Oh, right, I see.
In order for an infinite sum to be takeable, that common ratio precisely must fall between 0 and 1 for it to converge. And here we're being asked to add up every term. And so S sub n is going to be equal to the first term multiplied by nothing. Now, you'll notice that the infinite series equation is exactly the same as the finite series equation, but with one small manipulation made. And this is just so that it's easy to remember. It's the same thing as this. It starts off with the same proof, but here's the argument. Because this number is getting smaller and smaller and smaller and smaller, right? Every time I increase n. So if I had 1/2 squared, that's already at 1/4. And then the next time I add a term, it'll be 1/2 cubed, which is even small. Wait, what? Oh. 1/2 cubed, which is even smaller. And then if I do 1/2 to the, 100, that 100th term, we're already at something which is chased by 31 zeros before we add up another digit. And then I can also input this such that the calculator is like, yo, man, I can't calculate a digit that small. Oh, man, I'm being dumb. Sorry. It's supposed to be divided by. Yeah, even your calculator will be like, yo, that number is so small, we're just going to say it's 0, because the calculator doesn't have enough RAM to calculate how small this digit is. The argument is, if you have an r, which is a fraction between 0 and 1, and you keep increasing that exponent again and again and again and again, this whole term is going to stop contributing. This is going to become 1 minus 0, which is just 1, and then a sub 1 times 1 is just itself. So if you are asked to do this infinite series thing, yo, it's just a sub 1 divided by 1 minus r. This whole thing is gone. It is 1 minus 0 times 1 is just itself. And so, oddly enough, even though this seems like the fanciest request out of all of these, it's the least mathematically rigorous. The infinite sum here is going to be equal to the first term, 200, divided by 1 minus 1/2. And so if you take this series and you add up all of the digits in it, the infinite sum is 400. Which has a bunch of nasty ramifications if you think about it. Let me put some of those nasty ramifications inside of your brain. What I'm telling you right now is that even though it's hard to imagine, if you took this and you kept going, right, you would get 25, and then you would get 12.5, and then you would get 6.725, right, again and again and again. Yo, what I'm saying is this thing adds up to 400. So 200, 300, 350, the first 3 digits add up to 350, and that means that this next digit and all of the digits that come after, in grand total, all of those values add up to just 50 more. This type of information is determinable when you have a converging geometric series. I know it feels unnatural, but all of it is true. Is that okay?
Mr. Robinson,
Yes.
can you explain how you got the notation, the sigma notation for the geometric sequences or series one more time?
That is vocab. And actually, this one is technically wrong. This is supposed to be n minus 1. The thing that generates a geometric series is the fact that every single time we multiply by that common ratio, is to say that this function that is generating this is actually an exponential. It has a common base of our common ratio, which is being increased each time, right? So if you multiply by the common ratio 3 times, it's actually r cubed. If you multiply by the common ratio 4 times, it's actually r to the 4th, which is why these take the form of an exponential equation. The common ratio goes inside of the parentheses because that's the base of our exponential. The first term goes out front, and the exponent is n minus 1, so that this has the nice feature that when I plug in n is equal to 1, 1 minus 1 is 0, the common ratio raised to the 0 is just 1. And then that first term times 1 gives us back what the first term should be. So that's why this is 1, because this is the first term. Plug in 1, n minus 1 is 0. This becomes 1. 1 times 1 is 1. and that gives us the correct first term. And then this is saying every time you increase by n, multiply by 3/2. The same is true here. So 200 times half gives us 100 times half gives us 50, and so 200 is our first term times 1/2 to the n minus 1, so that when I plug in 1, our first term is 200, and then it correctly generates the rest of the terms.
Thanks, I got it.
So yeah, this is basically all of the notes of the section all packed into a single warm-up. These are the 3 types of questions which are answerable by the techniques in this section. Are there any questions on these 3 questions in the warm-up?
Yeah, Mr. Robinson, for the third equation, why isn't there a 1 minus r to the power of n in the numerator?
Okay, I'm going to talk about that one more time. So here's our regular old infinite geometric series. S sub n is equal to a1 times 1 minus r to the n divided by 1 minus r. And I actually think understanding where this equation comes from is way more difficult than understanding where the infinite version comes from, because the proof that generates this is hyper elegant. Like, you only know to do the manipulations that make this equation true if you already know what it is. This is one of those things where the dude who thought this up must have been wicked smart to have even had the intuition to go there with this. However, if you can accept this is true, like if you already know that this is correct, then this next step is I don't want to say trivial, but if you can accept that this part is true, then here's the next part of the argument that takes us to the infinite version. So for the infinite version, for S sub infinity, right, this is only generatable. So this is going to require that if r is in between 1 and 0, right, it's going to make the infinite version here calculable. And that is because for this to be calculable, this thing needs to be convergent. In every single step, it has to get smaller and smaller and smaller for the argument that I'm about to say to work. So if r is some sort of fraction between 0 and 1, and we're taking this and we're raising it up to the n, the argument is as n goes to infinity, then r to the n goes to 0. R is some fraction. So every single time I take it and I increase its exponent by 1, it's going to make that thing smaller and smaller and smaller and smaller. So clearly shown, right? Give me a fraction.
5/7.
Sure, that works. That's between 0 and 1. So if my equation, my generator is 5/7 raised to the x, and then I generate a table of values here, as we get bigger and bigger and bigger in our exponent, which is x, our output gets smaller and 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 smaller. And it does so not slowly, but quickly, right? This goes to 0 crazy fast. So by the time that we're at 50 or whatever, we're already in a place where before the first digit of this number, there's 11 zeros. Before the first digit of this number, now we're at 12 zeros, 13 zeros, 14 zeros, 15 zeros. There's just more zeros than there are actual values, right? So already by the time we're at our 100th term, this isn't going to contribute anything to our sum. It's going to be 15 zeros of blank space and then a digit. So when I take that and I add it back to the grand total sum that we have, it's not going to cause the digits that are in the first place or the 10th position to increase. So as n goes to infinity for this particular type of series, if it's convergent, then our argument is that, well, okay, this is going to be equal to a sub 1 times 1 minus r to the n divided by 1 minus r. But as n goes to infinity, this is going to go to 0. It's going to get so small that it doesn't matter as it contributes to our sum. And so s sub infinity is going to be equal to our first term times 1 minus 0 divided by 1 minus r. 1 minus 0 is equal to 1 divided by 1 minus r. And 1 times anything is itself. So long as you meet that first criteria that you are talking about a converging series, then this will always give you the infinite sum. It's just the first term divided by 1 minus the common ratio.
I got it. Thank you.
Yeah, but like I said, the hard part is understanding where this comes from. That's the part like worth understanding. Okay, so I'm going to do a little bit of supplementary notes on this section, just so that we're like a little bit more clear on what it is that we're doing here, and then we'll head out. I already mentioned on Classroom, in case y'all didn't know, that based on the results of that poll, that everybody voted to move the quiz, which personally I think is the wrong decision for all of you, but you know, live your life. We make mistakes and then we learn from them, because that means that instead of just like, I don't know, taking a quiz with those first 3 sections and these 3 equations on Wednesday and getting it out of the way, you guys get to go off to 2 weeks of AP tests, and then at the end of the second week, we get to review and have a quiz on Friday. Just know that that is the scheme. So that means that today, tomorrow, and Wednesday, we're just doing workshop on this stuff. By Wednesday, I'll post the review assignment. You guys will go away and do AP tests. And then next week on Thursday, at the end of the second week of AP tests, that Thursday, we'll meet for 1 day of just discussion to talk about what's going to be on the quiz. Quiz is next Friday. Some information about infinity. So infinity is an extremely complicated mathematical object, and the reason why I say that it is an extremely complicated mathematical object is the fact that it is not a number. So infinity is not a number in a traditional sense. And so there are several things that we cannot do with it. So you'll notice that here in the previous part, when I was explaining this, right, I use the language and I say, as n goes to infinity, then r sub n goes to 0. Because it's not a number, I can't use it like a number. So you cannot do the following things. You cannot say that n is equal to infinity. Nothing is equal to infinity. That's part of the definition of infinity. You can't equal it. It's too big. And you also can't substitute it, which is to say I can't simply say that r to the infinity goes to 0, or sorry, equals 0. Again, this is a no-no. You can't substitute it. There is no substituting it. There is no setting it equal to stuff. It is too big to equal. Now, we can say that numbers approach infinity. Numbers can get close to infinity. Like 1 trillion is getting there, a quadrillion is getting there, a Google is getting there, a Googleplex is getting there. But if you can state a number as a word, or if you can state a number as a digit, infinity must be bigger than that by definition. By definition, it has to be bigger than that. It's too big to equal. And also because it is a number, it cannot be substituted into equations. Okay. And even deeper than that, there are actually various types of infinity. So infinity comes in various flavors. Or types or what have you, where depending on what exactly is going to give you back your infinity, we have different descriptions and different rules for how those infinities behave, should we manipulate them mathematically. Now, there's actually 6 or 7 different types of infinities, depending on whether or not you're talking to a mathematician or a physicist. But here are the 2 simple examples of 2 different types of infinities that we could describe for the sake of precalculus. So you'll notice that when it comes to arithmetic series, right, that in our arithmetic series, those are only finite. They're only defined for finite values. And here is why. Let's say that I were to ask you to add up an infinite number of numbers from the first term to the infinitely final term of the following sequence, 2n plus 1. What is this asking us to add up? Like, what would our first digit here be?
3.
Plus?
5.
Plus?
7.
All the way off to infinity, right? And so if you added up an infinite number of positive numbers, what do you think you would get? What's a way that we could describe this? Are we going to get a big number or are we going to get a small number?
Big number, obviously.
We're going to get a big number. How big?
Infinitely big. You
Right.
can't define it.
You are going to get an infinitely big number if you keep adding numbers to this forever and then not ever stopping. This is going to give us back infinity, and I'm going to put it in quotes because technically you can't set anything equal to infinity, but yo, this is going to blow up, right? This is going to very quickly get so big that we can't actually keep track of what this digit is. However, if we were to add up the following from n is equal to 1 all the way up to infinity of the following geometric series, 2 times 2 to the n minus 1, what is this asking us to add up? What's our first digit?
2.
2 plus 4 plus, what's the next digit?
8.
Plus
16.
plus
32.
All the way down to forever. Now, what is this infinite sum going to be equal to? Can we calculate that?
No.
No, we cannot. When it comes to our infinite geometric series, we can only do that if the thing itself converges, right? Which is to say our common ratio has to be a fraction. It has to fall between 0 and 1. And so this one is not converging. This diverges because the common ratio is greater than 1. And so this is also going to add up to some infinitely large number that we cannot process. However, these two are not on equal footing, are they? Like, which one of these do you think grows faster?
The second equation.
Right, this second equation is growing way faster. And again, if you were to think about our family of parent functions, arithmetic series describe linear functions. So this one is growing linearly in a way that we can predict with a slope of 2 and an intercept of 1. But geometric equations, they grow exponentially, right? And so each step, the number that we're adding gets bigger and bigger and bigger and bigger to the one previous. Even though both of these we say go to infinity, right? We can't actually process what any of these values are. And so in order to differentiate the behavior of these two different types of infinite sums, this is what we refer to as a countable infinity. And as such, there are certain manipulations we can do with this series in order to change the outcome, simply because this infinity can be tied to a steady growth rate that we can measure. Whereas down here, this is growing quicker than we can describe. This is just going to blow up. And it, like, very quickly, you'll be adding numbers to the series which overwhelm the series itself, right? You'll be adding numbers to the series that are bigger than the sum that you have at any given moment. And so this is referred to as an uncountable infinity. And again, if you wanted to do manipulations with this series, there are things with it that you can do and you can't do based on the various categorizations of infinity. So infinity itself, not a number, nothing can be set equal to it. You can't even actually plug it into equations in the normal sense. And to make things even stranger, there are multiple different flavors of infinity depending on exactly what is generating the infinitely large value that you were talking about. The only intelligible treatments of infinity, just so that you guys know, the only useful treatments of infinity come from calculus and statistics. And the nifty trick that we use to derive the infinite geometric series equation, saying that some decreasing fraction raised to the infinity is actually 0 or goes to 0 quickly, is the majority of how you will treat infinity in the future, where it produces real answers for you. But there will be entire sections in calculus and in your future statistics courses that deal with the various types of infinity. Is that stuff okay?
Yep.
Okay. And so knowing that all of the other types of infinities are not calculable, let me give you all a little bit of motivation for how it is that infinite geometric series are calculable. And I think what's interesting is the fact that the ancient Greeks figured out the infinite geometric series stuff, but all of the other math that you might do with infinity led to contradictions and stuff in math. And so literally from like minus 300, when they figured out how to add up an infinite geometric series, all the way up until Isaac Newton, mathematicians were just like, yeah, we don't mess around with infinity. It leads to like nonsense statements. And then like when we invent calculus, we figure out how to resolve all of the contradictions caused by infinity itself. So a little bit of information of like, how is it that an infinite geometric series is possible? So some ways to think about infinite geometric series. So today in the warm-up, we had 200 times 1/2 to the n minus 1, and we added up all of the digits there. So if you sum all of the digits from 200 and 100 and 50, so in the warm-up we saw today that 200 plus 100 plus 50 plus 25 plus 12.5 ... If you take this all the way out until there's an infinite number of digits, the sum of all of this garbage is equal to exactly 400, which I think is strange. Let me try and justify this a couple different ways. Number one, this thing right here is starting off at 200, right? That's where it would cross this axis. And then it is decreasing exponentially. So this is 200 here for this if we're graphing a sub n's versus n itself. And this is a decreasing exponential function. So as we go off to the right here, right, it's going to get smaller and smaller and smaller and smaller. And what do we call this type of behavior? What fancy word did we have there?
Asymptotic.
Yeah, so the asymptotic behavior, is what causes it to converge. This thing is asking us to take a step forward and every integer, add that number to the number previous. So here where we cross the axis, that's at 200. And then at the next step, it's asking us to add back to that 100. And then at the next step, it's asking us to add back to that 50. And then at the next step, it's asking us to add back to that 25. And then at the next step, it's asking us to add back to that 12.5. The argument being that eventually these numbers that we're adding down here, right, by the time that we're out here where the fractions are hella small, so by the time we're here, this is adding 0.000 something, 0.001. And if you take that and you re-add it, at the point that you're adding digits this small, we're already at a current running sum of 399.9996 or whatever, on our way out. If you add this number to that number, this decimal is going to be in a position where it will never be large enough to cause our total to ring up. So the deal here is that if I added 4 in this position, the 6 would become a 10, and then that would add 1, that would add 1, that would add 1, that would add 1, and then we would suddenly be at 400. The deal with geometric series is that this number is shrinking. This thing right here shrinks faster than the sum grows. And as a result, by the next digit out, this will be one spot over. And again, it will be too small to cause this to ring up again. If you were to do this manually and you were to keep adding digits, 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 you would actually only ever have 399.99999999999. The only thing that allows us to have it ring all the way up to 400 is by doing the math that takes it from 1 to infinity. Nasty, huh? Isn't it fun to talk about math when we can't do algebra that shows our arguments, but we only have like ration? Here's another.
So,
yeah.
Mr. Robinson, are you saying that it infinitely approaches 400?
Yeah, that if you were to like add up the first 100,000 digits with a calculator or with an Excel spreadsheet, you would still only get 399.9999999, and it only ever truly gets to 400 if you do the mathematical trickery that takes the infinite sum.
Oh, interesting.
Yeah, it's wild. Here is another way that I have seen this idea described that I think is really nice. So do y'all see this square?
Yeah.
Yeah.
So this is why it's called a geometric series, because the arguments for this come from the ancient Greeks who, you know, like they were busy, like, I don't know, fighting the Persians and drinking a bunch of wine and worshiping Bacchus, or like writing fan fiction about Zeus, because back then the Greek gods were all they had. They didn't have regular superhero movies yet. And when they were not doing any of that regular ancient Greek stuff, they were making geometric arguments by scratching stuff in the sand and teaching the youngins, and we still have their math today. The reason why it's called an infinite geometric series is that information about these geometric sequences can be reproduced using pure geometric arguments, and here's the geometric argument. If you take all of the terms that are generated by the sequence, 1/2 to the n minus 1 times 1, right? So this would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/30 plus 1/64. You are taking a square or a rectangle, which is precisely 1/2 of the size of the previous rectangle. So our first rectangle has an area of 1/2. Our next rectangle has an area of 1/4. Our next rectangle has an area of 1/8, an area of 1/16, all the way down. You can take those and you can take every single one of those rectangles and squares and fit them into a square. And no matter how tightly you fit them, there is always space in the top corner for the next term in the series. Always. This is an argument that shows that as long as you are adding elements which get smaller and smaller and smaller and smaller that decrease to this amount, the grand total is actually calculable. It all fits within a finite space that we can describe. And here's what's even wilder. The area of this square, guess what it is?
1.
In this particular case, it may be 1, but you can use arguments to show that the area of this square, based on what generates it, is exactly the same as this equation. That if you took the two side lengths of that square based on how they're written in terms of the sum, the area of that square must be precisely proportional to this, because one side length of the square is A1. The other side length of the square is 1 divided by 1 minus r.
That's crazy.
Yeah, that's math with infinity. And don't get me wrong, this is confusing. This should hurt your brain, because I don't think you guys have ever thought about infinity before. But the reason why we talk about it now at the end of pre-cal is that this is pre-calculus, and all that y'all are going to be doing for the first few months of calculus is finding rationalizable ways that we can talk about infinity, intelligent statements that we can make about a number that grows bigger than we can actually capture. And even when we're done with this chapter, when we do our final chapter of the year after the chapter 11 chapter test, we're going to begin calculus. And at the end of this year, we will come back on some other ways that we can think about infinity intelligently. Nonetheless, that's the end of class today. I just wanted to flush this out because last week on Friday, we literally ended here. And then I was like, okay, bye everybody. So I wanted to make sure that we got a chance to talk about like, what is this actually talking about? How is it that you can add up an infinite number of numbers? The understanding of this is fuzzy for everybody up until you do a bunch of calculus. With calculus, I can show you that this is precisely true. But for right now, we just kind of have to accept these arguments as they are geometric. You have to accept these arguments for the same reason that Greeks 2,300 years ago accepted these arguments. But in calculus, you guys will find how we worked our way out of the contradictions inherent here. You all have a nice week. Good luck studying for those AP tests. And I'll see you tomorrow for workshop. Tomorrow we'll do review for the mid-chapter stuff, and I'll give you the review assignment. And then Wednesday, we'll mostly just chill. In reality, on Wednesday, we'll probably just head off early. Take it easy. See you tomorrow.
Thank you, Mr. Robinson.
See you, Mr. Robinson.
Mm-hmm.
Bye.
Bye.